First one, TA will post a PDF form solutions to the midterm online in this way. Okay, we'll not go over it, just post the solutions online. And the next Monday, next Tuesday and Thursday, or Wednesday, Thursday, we have a field tour. Don't forget it. Also, bring your ABET evaluation form to me next Monday during Dr. Ubadaya's lecture, okay? And any question for the field tour or any other things, stuffs? Okay, no? Okay, good. Tonight's class is a new format with a guest speaker to, not me. Not me, right? To introduce data-driven methods for prognostics. Dr. Jamie Coble is an assistant professor at the Department of Nuclear Engineering. She graduated from University of Tennessee with PhD in nuclear engineering in 2010. Then she worked as a research assistant professor for a while on campus. Then a scientist at Pacific Northwest National Lab for 2 years. In 2013, Dr. Coble moved back to Knoxville, start her new position on campus. And Dr. Coble's research interest focus on empirical modeling methods for process and equipment monitoring, anomaly detection and diagnostics, and prognostics. So please join me in welcoming Dr. Coble for her presentation.
Thanks. So I'm going to talk a little bit about, really more about my research and an introduction into what data-driven methods for prognostics entails, what it includes, and we'll talk a little bit about how that feeds into reliability and maintainability. But really, if you're thinking about prognostics, it's really just a stepping stone to doing condition-based maintenance. So the reason that we're interested in doing condition monitoring and prognostics is just to do better operations and maintenance planning. So the crux of what we're thinking about, we have data that we're measuring on our system, our components, whatever. You're measuring data all the time. You know, if you think about any kind of large industrial facility, nuclear power plants in particular are very highly censored. So you have lots and lots of redundant information. And we have all this data that we can use to control our system to make sure that we're, you know, if you're in a nuclear power plant, you're making the electricity that you want to, and everything is safe and reliable from a being on the grid standpoint. But we can also use those same data to evaluate the system as a whole, to say what's the condition of the process, but also what's the condition of the equipment that's controlling the process. And so we want to use all of our available data, which could include process parameters like flow rates and pressures and temperatures, as well as equipment data. So maybe you walk around every couple of weeks and take vibration measurements on your rotating equipment. So we want to combine all of that information together and kind of discover what the underlying relationships in our data are. And so how can we use the data that we're collecting, do some statistical analysis, and infer the condition of our equipment, decide when we need to do maintenance, what kind of operations we can do, what kind of controls we need to look at. And so all of the methods that I'm going to talk about are going to be data-driven methods. So they all rely on the data that you're collecting from your system. There is a separate class of prognostics algorithms that are physics-based, where you have to develop a high-fidelity physics of failure model for your components in your system. That's very challenging to do. One thing, we don't understand the physics of failure for a lot of components. For another thing, if you do understand it and you build a high-fidelity model, often that can't run in real time. And so computationally, we can't really use those models to run while the system's running to make decisions. So for those reasons, we kind of fall back on data-driven methods that kind of naturally capture what's going on in our system. So probably everybody's already taken 483, so you're familiar with the concepts for reliability. Reliability pretty much just says if I have a whole population of components, how long are they going to last on average, under average conditions, right? So under average usage, what's the average lifetime of my components, and you get a nice distribution, and that kind of tells you for a population, what's it look like. but we're not actually interested in the population, we're interested in a specific component. And so prognostics extends that idea to look at what's the lifetime of my specific component under the operating conditions that I'm imposing on it. And so we want to know kind of when is the thing going to fail, or what's the probability that it's going to fail over some mission time. You know, what's our confidence that it won't fail, that it'll continue to meet its design specifications while we need to use it. And the benefits of knowing when something is going to fail are pretty obvious. Like, you know, you can run right up until failure. So instead of doing periodic maintenance where you're kind of giving away a lot of your useful life, we can run our equipment right before failure and then stop and fix it. So we get as much useful life out of our equipment as possible, but we also prevent or lessen the probability of in-service failures. So you know what the condition is, you know how it's evolving over time, and so you can fix it before it fails. So if you think about, if you set a periodic maintenance interval based on the average lifetime of something, then half of the things are going to fail in service and half of them are still going to be fine when you fix it. And so we're kind of avoiding both of those basically costly maintenance practices. So prognostics, and we'll kind of hit this point a couple of different ways. So prognostics is just one part of our overall equipment surveillance system. And so, like I said, we start with data. We're measuring things on our system, measuring features of the equipment directly. We're going to monitor that data and say, can we detect that something's changed? So we're just looking for, is something different than the way I expected it to be? Is there some kind of anomaly or drift from the expectation? If you detect that something's changed, why did it change? Can you diagnose the root cause of the fault? And then based on that diagnosis and how your measurements are evolving over time, you can prognose the remaining useful life. So how much longer can I go before the thing's going to break? And then kind of the key is, how do I then mitigate that? So how do I tie that back in to extend the lifetime? So if we think about, we have some system, nuclear power plant or some industrial system, your car, whatever. You're collecting data about that system. You develop a monitoring model for your data. So this model we can think of as typically as an error correction routine. And so it's going to tell us, based on the way you're operating your system, this should have been the set of measurements that you got. And so it's going to say, you know, regardless of what you actually measured, this should have been your measurement. And then you compare that to what you actually measured to look at the residuals and do some fault detection, fault diagnostics, prognostics, which will consider all of these things, the data, the model residuals, the fault diagnostics and false alarms, and then you get the remaining useful life out. So how much longer can I operate before something's going to break? And then, you know, again, ideally you take that remaining useful life information, feed it back through your operations and maintenance planning or your control, so maybe you can reduce the load on your pump and make it last longer than it was going to. And so by changing the way you're operating, you're affecting your plant, you're affecting your remaining useful life, and so you can extend to a convenient time to do maintenance. So if we look at these data, this is data from a turbofan engine simulation that NASA has. So it's all simulated data. For a turbofan engine, the cycles are basically flights. So for every flight that this engine took, there's one observation of data. And it's a combination of operational conditions, so what was the altitude, what was the speed, as well as some measurements from the system. And if we look at this data, it starts at the beginning of the engine lifetime, and at the end of the data, the engine failed, right? So this is the entire life cycle of the data, from beginning of life to failure. And if you just look at it, there's nothing really obvious going on. To my eye, it just appears to be steady state. So it doesn't look immediately like anything's changing. But if we develop a kernel regression model, just a very basic, very simple weighted average type of model, and look at the residuals between what we measured and what we expected to see based on our, you know, the performance during good operation, now you start to see that there is something going on. We have these nice trends that start somewhere around 100 flights and rapidly go down to failure, right? So when we look at our monitoring system residuals, things that were not immediately obvious in our data become like crystal clear. And so then we can take these residuals, combine them together. Our residuals kind of naturally tell us how far our system is operating from expectation, from normal operation. And so they naturally give us an indication of the condition of our equipment. And so we can combine those together to get one single parameter, one single vector that tells us what the condition of our equipment is and how that's evolving over time. And so for one engine simulation, this would be the prognostic parameter over its entire lifetime. The goal, though, is to get a population of prognostic parameters that look the same across a population of engines. So if we have 200 some odd engines that all failed due to the same failure mode, their prognostic parameters should look pretty much the same. So that now when we start to see new data, then we start to see our new data, we know kind of what it's supposed to look like, we know where it's supposed to fail, so now we can fit a line to the data, extrapolate it out to where it's going to cross this failure threshold, accounting for noise and uncertainties and things, and get a nice distribution of when this particular engine that is still early in life is going to fail. So that's the whole idea behind prognostics. Can we monitor something about the system that will tell us what the health is, how the health is changing over time, and allow us to estimate the remaining useful life? Okay, so prognostics, typically in this instance, we're going to talk about prognostics as a way to estimate the remaining useful life of your equipment. Usually this doesn't mean that your equipment has catastrophically failed. We're looking at soft failures, so we want to fix things before they explode in place, right? We want to fix it when we just no longer are confident that it's going to meet the design criteria. And so remaining useful life may not necessarily mean that the thing is, if you ran it for another minute, it was going to completely disintegrate. It just means that we're not very confident that it's going to keep working the way we want it to. The remaining useful life and the time of failure differ only slightly. The time of failure is kind of absolute from beginning of life. The remaining useful life is the time between now and the end of life. So the remaining useful life is just time of failure minus the current time. Okay, and so we have three types of data-driven algorithms that we talk about, or three classes, really, of data-driven algorithms. And it really just depends on what kind of information you have available for doing your condition assessment and prognostics. If all of the information you have is historic failure times, then we call that type 1 prognostics, which is just reliability analysis. So we're just doing reliability analysis based on when we've seen things fail in the past, find a distribution, and do your traditional reliability that you've all already probably learned about. If we can measure something about how the equipment is being operated, so what are the environmental stressors, what are the loads that we're putting on the equipment, the demands that we're taking from the equipment, then we can do type 2 prognostics, which is taking into account how your system is being operated. So type 1 prognostics is an average component under average conditions. Type 2 prognostics is an average component under specific conditions. And then type 3 prognostics is when we can actually measure something from the component that allows us to either directly measure the condition or infer the condition based on what we're measuring. And so we have kind of a natural progression between type 1, type 2, type 3, but the ultimate goal for anybody who's trying to do condition-based maintenance is really to get to type 3 prognostics. So if we think about an example, if you buy some car tires, when you go buy new tires for your car, they'll just tell you these tires are going to last 40,000 miles. Maybe it's plus or minus 5,000 miles, but that's a type 1 prognostic, right? They're saying on average, they've done a whole bunch of accelerated life tests, and on average, they found that under normal usage conditions, those tires last 40,000 miles. Now, if you take those same tires and put them on, like, say, your grandmother's car, certainly my grandmother's car, and she's driving, to the grocery store once a week, and that's about it. That distribution is going to shift. So maybe now those exact same tires would last 50,000 miles instead of 40,000 because she's driving very conservatively, and so she's not putting extra wear on her tires. If on the other hand you put him on like some 16-year-old kid's car and he's like jumping off at green lights and going off-roading and doing whatever, then it's going to shift it down. So now instead of lasting 40,000 miles, maybe those tires only go 25,000. So this is, in a very simple case, type 2 prognostics. We're considering how are we operating our tires and how does that affect the lifetime. And then finally, let's say we stop every 100 miles and measure the tread depth. And you measure the tread depth and you I guess this would be like the inverse tread depth. But so you measure the tread depth and plot it out and say, okay, how's this changing over time? Fit a line to it and extrapolate it out to failure. So type 3 prognostics. So it's kind of, in the tire case, this is not really practicable. You're not going to stop every 100 miles to measure your tread depth. But if you had some automated sensors that could collect that data for you while you're running your tire, or maybe you're monitoring your tire pressure or your operating temperature of your tires, things like that, then you could infer the health of your tire. So, like we said, the basic data requirements, if you have type 1 reliability-based prognostics, you just need a population of failure times. You just need to know in the past when have things failed, and that's all you need. Once you, to move to type 2 prognostics, you have to be able to measure environmental conditions and stressors on your system that are somehow related to how it's going to degrade over time. So not only do you have to be able to measure it, but it has to be relevant to what you're doing. And then for type 3 prognostics, you have to be able to measure something actually on the system. So if you think about your component as a black box, type 2 prognostics, you're measuring what's going into the box. Type 3 prognostics, you're measuring something coming out of the box. Okay, so I'm going to run through some different types of algorithms and just follow this example application just to illustrate what I'm talking about. In 2008, the IEEE had a prognostics and health management conference that included a challenge, and this is where that turbofan engine data came from. So NASA simulated a lot of turbofan engine data. They didn't tell us what the data was, so it was just blind data. They said, here's a bunch of data, it's time series data, good luck, right? And so we had 3 operating condition indicators, 21 sensed variables, and we had 218 cases from beginning of life to failure. So we knew the failure times for 218 engines. And then we had another 218 test cases that stopped sometime before failure that we could use to train algorithms, and then a final 435 final test cases, which were what was actually judged to evaluate the system, or to evaluate everyone's prognostic models. If anybody's interested, these data are publicly available on the NASA prognostics data repository, along with several other prognostics relevant data sets, so you can download them and play around with them if you want to. So just to go through some data-driven approaches to doing prognostics. Again, type 1 methods are just reliability. It's just doing traditional reliability analysis. And so we had 218 failed cases. We knew the lifetime of 218 engines, so we could make a reliability, we'd fit a distribution to those and do traditional reliability. And so you just estimate the failure density function using parametric or non-parametric techniques that hopefully, if you haven't already taken 483, when you take it, you'll learn about. And then when you get a new system, I'm kind of jumping ahead of myself. So hopefully everybody already knows this. I don't want to waste a whole lot of time. But so typically we use a Weibull model to fit reliability data. Is everybody familiar with Weibull models? Yeah. Okay. So we'll skip through that. Okay, so then once we have our reliability distribution, then if we want to use that to do prognostics, you have to account for the fact that you've already run for some amount of time. And so at the beginning of life, your remaining useful life estimate is going to be maybe the mean failure time from your distribution. But as you start running, then you have to look at the marginal reliability function. So it's just the reliability at time t, given that you've already run up until sometime capital T. So we can just solve this equation to find out where at what time our reliability function is below some threshold that we're interested in. Perhaps you want it to be 95% reliable, perhaps 50%, depending on how important the component is to your operation. But basically, we're just going to find the time where our inverse reliability function is 1 minus alpha times the reliability at the current time for t greater than the current time. So it's a very straightforward calculation, but what you can notice here is the only thing that we're considering is how long our current system's been running. And so it's not going to give you very much information about your actual system. Again, it's just an average component operating under average conditions. And for the PHM challenge data, as expected, this doesn't work very well, right? You wouldn't expect this to do very well. You can see we have a nice, if this dashed line is our 1-1, you know, what we want our predictions to fall on, they're just kind of randomly spread about that line, which is what you would expect. Again, it's an average, and so half the time it's going to be too high, half the time it's going to be too low. And that's kind of what we see in practice, and that's pretty much what you always see in practice when you apply reliability to a specific component instead of to an entire population. And so, since the operation of our different turbofan engines could be very different, which we could kind of characterize based on our 3 operating condition indicators that they were reporting, then we can move to type 2 prognostics, which is looking at an average component in specific usage conditions. And there are a whole bunch of different ways to do type 2 prognostics. We have kind of stressor-based reliability models where if you can assume that your system is only going to operate under one condition for its entire lifetime, then you just make different reliability models for every operating condition and apply those. That's usually not a very good assumption though. So then we have proportional hazards models, life consumption models, Markov chain Monte Carlo models. So these things are trying to capitalize on the fact that we know something about how it's operating and that that's related to how it's going to degrade. And that's the key issue. You have to be able to measure something about how it's operating, and that thing you measure has to be related to the degradation. So, like I said, the simplest method, if you don't know, or if you know that you're just going into one operating mode for your entire life, such as putting your car tires on a 16-year-old kid's car versus an 80-year-old grandmother's car, you can just have separate reliability distributions. And so this will be a little bit more specific than the big lumped reliability model. If you lumped all of these together, then you're going to get a big spread out thing, and it's not going to capture what's really going on. But more realistically, we have things like the proportional hazards model. I'm not sure if you covered this in 483, but so the proportional hazards model capitalizes, so it's just looking at the failure rate as a function of the original failure rate and some function of how you're operating. So a function of your covariates. So your covariates could be the speed at which you're flying, the altitude, the temperature, the ambient temperature outside, things like that. And so the assumptions here are that we can find a baseline hazard rate, lambda naught, that only depends on time. So lambda naught could be a function of time, but doesn't depend on anything else. And then we have a second function that only depends on your operating conditions, so your covariates. And then that your actual hazard rate is just the product of those two things. So if all of that is true, then we can apply the proportional hazards model, which will take your baseline failure rate and convert it to whatever is relevant for your system, the way that it's being operated over time. And we just use regular maximum likelihood estimates to figure out what all of our parameters for our covariates are. And then once you have that, you just have a hazard function. You have your failure rate, and so you can just solve it with the regular approach to hazard functions, right? Your hazard function is just the integral of your failure rate, and then the reliability is the exponential of your hazard function. So, and then you go back to the same, when you want to find the remaining useful life, go back to the same marginal reliability, given that you've lasted up until time t. Okay, so unfortunately in this case, again, it does a good job of not underestimating the remaining useful life, wrong way. So we don't overestimate the remaining useful life, but we underestimate it a whole lot. So we have a lot of high remaining useful life that we estimate is roughly 0. But in general, we're kind of below our remaining useful life 1-1 line. Given, and here you used a reliability cutoff of 95%. So, and we'll see in a second kind of why that is. Another option is to look at Markov chain models. Is anybody familiar with Markov chains? Yeah, so the Markov chain, we're just assuming that we can transition between states and our transition only depends on the state that you're currently in. You don't need to know the history of where you've been. And so we can kind of use the historical data, how we've historically operated, find out what this transition probability matrix is, or if you have a non-discrete space, what your transition function looks like, and then use that transition probability matrix in a Monte Carlo simulation to simulate a whole population of potential routes to go from beginning of life to failure. And so you have a population of potential degradation paths, and then you can look at distributions of that degradation path. So again, it's kind of two models. We have a model that uses the transition matrix to determine, in a Monte Carlo sense, like what states do you operate in, what's the order of states, and then you have another model that maps those states to the condition of your system. And so the very simple approach is just to say that the condition is just the sum of the amount of degradation that you gather every time you're in a specific state. So you can just say it's kind of a linear increment of degradation, and that's typically what people apply, although you can easily do a much more interesting and complicated model. So here, if we look at this, if we start at time 0 and we have a Markov model of how things are going to evolve over time, if we start at time 0 and just simulate a bunch of paths and say, okay, what's our time 0 before we've actually started operating? What's our distribution look like for the total lifetime? And then as we collect a little bit of data, so now we've operated one cycle, we know exactly what our first operating condition was. Starting from there, we re-simulate a new path, and you get a slightly different distribution. So every so often you can stop, re-simulate, redo your Monte Carlo simulation, and reevaluate your failure probability. So here, after 100 cycles, then we stop and re-simulate what all of our failure paths are going to be based on, we already know how we've operated for the first 100 cycles, so we just convert that to our condition index and then re-simulate. You can see we have a much, not only is our failure distribution shifted over, but it's also much tighter, which is kind of what we want to get to. You want to have a higher confidence in your remaining useful life. And then as we get very close to failure, again, we have it's shifted over a little bit, but it's also much tighter. And so we had for this, the problem, and this is really what we saw with the proportional hazards model too. For this data set, we had 6 distinct operating conditions, and it was pretty evenly split between all of them. We had about a quarter of the time in operating condition 6, but all the rest of the time you were pretty much in any one of the other 5 operating conditions equally, and your probability of going between operating conditions was pretty much the same. So, if we read this chart, this number here is the probability if you're in state 1 that you stay in state 1. If you're in state 1, if you're in state 2, the probability that you go to state 1. If you're in state 3, the probability you go to state 1, and so on and so forth. And so there's not a lot of information that you can glean from that. It's pretty much just consistent across the usage of all of our turbofan engines. And so this is ended up actually not being very well suited to type 2 prognostics. And then if we look at how well the time spent in each one of those operating conditions correlates to the total lifetime, you can see that it does not. And so, again, that's kind of why the type 2 prognostics didn't work. We're falling behind on one of our, we can measure things about how we're operating, but it's not correlated to condition of our equipment. And so for this data set, and the problem is that it's very difficult to manufacture data sets where you can use them for all 3 types of prognostics. But so for this data set, we don't do very well with type 2 prognostics. And here for the Markov chain Monte Carlo method, you can see it pretty much looks like the type 1 prognostic model. It's just kind of random, spread around our true line. So then we go to type 3 prognostics. And this is the degradation-based prognostics. So now we're trying to find some measure that we can use to infer the condition of our specific engine under the way that we're specifically operating it, and how do we expect that to evolve through time. And so again, we can use Monte Carlo Markov chain methods. We have shock models, which are very similar to the Markov chain, which I'm not really going to get into. The general path